So this is the Fourier series part 6 lecture for ECE 343. Today we're just going to go through two examples. We're going to go ahead and do some Fourier analysis, some Fourier series of some waveforms, and we're going to make use of properties to try to simplify the process of finding Fourier series coefficients. For the first example, I'm going to do a little preliminary math. This first example is not meant to be efficient. It's meant more just to demonstrate a wide range of properties in use. So this one's more for demonstration purposes of the different ways to use properties in these kind of problems, not because we couldn't find a more efficient way to do it. The second example I'll give is going to be one that's going to be done primarily with efficiency in mind. So this first one we're going to do is we're going to have a little bit of preliminary math. And I'll do this quick. We've seen something very close to it before. I'm going to go ahead and look at a DC offset square wave, but the only difference I'm going to do this time is I'm going to allow it to have a variable duty cycle. So we're going to go ahead and have it be a periodic waveform, right? And that period is going to be over some interval t naught. And the only difference now is instead of it being on for 50% of the time, I'm going to allow it to be on tau out of t naught of the time. So I'm going to call this whole signal, this is a function of t. I'm going to go ahead and call this signal, I'm going to use a little bit of crazy notation here, p sub tau comma t naught of t. So p, because it's a pulse waveform where tau out of t naught duty cycle as a function of t, right? So p sub tau comma t naught of t is a t naught periodic, right? Periodic. And we're going to have a tau by t naught duty cycle, DC offset, square wave. And what I would like to do is I would like to go ahead and find this guy's Fourier series coefficients. So the pKs are going to be gotten from the Fourier series analysis equation. So I'm going to have pk being 1 over t naught, and I'm going to integrate over a period. And if I look at this, I'm going to pick a period here that's just going to include that pulse over the first one. So I'm going to go from a value, if you want to call it here, minus t naught by 2 to t naught by 2. That's the interval I'm going to choose for my integration. It just makes things simpler. And over that, right, we know that the underlying waveform, little p, is only non-zero from minus tau by 2 to tau by 2. I've shown this as an even function where the pulse itself has width of tau. So it's going to go minus tau by 2 on one side and plus tau by 2 on the other side. So my limits of integration here are going to be minus tau by 2 to tau by 2. And what am I weighting there? I'm going to have a 1, and I'm going to have an e to the minus j k omega naught t dt, right? Something along those lines. It turns out in this particular case that the DC term is going to be exactly equal to what we are going to get for the non-DC term. So I'm just going to go ahead and work straight with this equation and solve it directly. We'll verify the DC just at the end as a last little step. So in this particular case, it's an integral of an exponential, right? Nothing wrong with that. And I'm going to get a 1 over t naught, and I'm going to have an e to the minus j k omega naught t over minus jk omega naught. There was really no need for us to worry about a separate DC term. Why? Because this front term up here, right, doesn't give us any kind of quandary one way or the other. There's no t's there or anything, nothing like an integration by parts or a change of the integral form. The integral form is always going to be here an exponential, of which DC is just one case. Okay, so I've done the integration. This is integration of an exponential, about as easy as it gets, and it's going to go on limits minus tau by 2 to tau by 2. If I go ahead and plug those limits in there, I'm going to get a little bit of an ugly expression, but I'm going to have a 1 by t naught, and then I'm going to pull out this 2 by k omega naught, pulled out a little extra 2 because I want a 2 in the denominator, and I'm going to have the limits here. I'm going to have an e to the minus jk omega naught tau by 2 minus e to the jk omega naught tau by 2. And I'm going to divide this whole thing by minus 2j. So I got that 2 in the denominator, right? I got this 2 in the denominator because I just put a 2 in the numerator in there. Otherwise, everything just comes out Furthermore, I've grouped those exponential terms together in a single way because I recognize that from Euler's as being a sine function. So a little bit of final cleanup here. I'm going to get 2 by t naught k omega naught, and I'm going to have sine then, right? K omega naught tau by 2. This dang near looks like a sinc function, but not quite. So if I, again, just clean up a little bit, if I write this as a sine, and I'm going to put the pi in there just because I'm going to use a MATLAB type notation here. That way it'll be easy to implement on MATLAB. And I'm going to have a k omega naught tau by 2 pi, right? I needed the pi out front just because of the way MATLAB defines a sinc function, so I put a pi in the denominator of my sine term. So that's the sine in the numerator. And what did I have in the denominator? Well, I need that same argument. So I need a pi k omega naught tau by 2 pi. Now I had the k omega naught, right? I had the k omega naught in there, and what I am missing out of all of this is that parameter tau and t naught. Well, I can get that in just by multiplying the front end by the reciprocal of those. So I'm going to get a tau by t naught out front, something along those lines. So let's just do a little accounting here. The first one, right, had in here a tau, right, and we certainly see the tau in there. We have a pi that I introduced, but I have a compensating pi down there. I had a k in the original, so that k is there, right? I had an omega naught in the original, that omega naught's in the original. Now, I put a 2 down here in this denominator, but that's a denominator of a denominator, so it really just came out of that numerator up there. And the only thing that I needed then left is this tau here, which I just compensated with that tau there. So I've just done a little bit of cleaning up. I've tried to get it into a form that I recognize so I can get it in terms of that sinc function. So what do I get? I get a tau by t naught, and now I have a sinc on the right side. So I'm going to get a sinc function, and because I'm using the MATLAB notation for how I express it, it's going to be k omega naught tau by 2 pi. If you were using a book notation, we would not have done that game with a pi. It would have just been sinc of k omega naught tau by 2, something along those lines. Okay, so out of all of this, this is my cap p sub k. So I'm going to just reclaim this or kind of re-mention it. So we have a p sub tau comma t naught of t, right? That's our tau by t naught duty cycle DC offset square wave, and it's going to have a set of Fourier series coefficients, p sub k, being equal to tau by t naught sinc, right? K omega naught tau by 2 pi, something like that. Now I'm just going to set this aside, right? I'm going to set this aside and call this a known distribution. We'll make use of this in our example that we're going to work on. So let's look example number 1, the main example for this. So we're going to take a look at a waveform. We're going to look at a waveform that I'm going to draw a couple periods out on. So let's go ahead and see if we can do that. I'm going to call this signal x of t. And I'm going to go ahead and start here at -1, and then I'm going to come out to 1, and then 2, and then it's going to repeat after that. Between -1 and 0, I'm going to let it go up 2 units, so this will be 2 in height. And I'm just going to let it linearly increase on that, right? And then from 0 to 2, I'm going to let it do the same sort of thing. It's going to be a linear, but it's going to be a linear decrease, and because it's a longer interval, the slope changes just a little bit, right? So it starts out kind of sharp, and then it ends at a more mellow kind of rate. And so we can just go ahead and repeat that, and it's just going to kind of do that forever. So this is a modified sawtooth of a wave. It's a modified sawtooth, and it's maybe not quite as sharp-edged. It doesn't have that jump discontinuity that the first sawtooth wave we've looked at, but it's still a sawtooth wave of sorts. So x of t is a piecewise constructed function, and it's got period 2. What do we know? Fourier series says, right? Fourier series says that our signal x of t can be represented as a sum of some Fourier series coefficient xk times e to the jk omega naught t. And so we're interested in finding those xk's. I'd like to find the spectrum of this signal. That spectrum is going to tell me the frequency content of the signal, and it's going to help me understand, what the frequency composition of the signal is like. Furthermore, I can use the Fourier series synthesis once I find those Fourier series coefficients, and I can reconstruct it just to make sure I get those coefficients right. In this particular case, the underlying fundamental Hertzian frequency is 1 over its period, so 1 over 3 seconds. We know that omega equals 2 pi f, and so that tells us that our omega naught is 2 pi by 3. Everything we do with our Fourier series is in terms of knowing the underlying fundamental frequency. So in this particular case, we have a fundamental frequency of 2 pi by 3. All right, so let's think a little bit about what would be involved in doing a Fourier series analysis equation for this waveform as drawn right now. We know that the x of k's, right, look like what? They look like a 1 by t naught integral over t naught, little x of t, and then I have an e to the minus jk omega naught t dt. If I just went directly to the calculus, I would have to put in the expression for x of t, which is a piecewise function, right? We know that that particular guy, this guy has 2 linear pieces, right? 2 linear pieces. So there's a straight line for the first part here, right? We'd have to get some equation for that line. And then there's another equation for this line. It's a different equation. And so we would have 2 linear pieces multiplying an exponential. So what would we get out of all of that? We would get 2 integration by parts. Right, there'd be 2 integration by parts there. Yuck, I definitely don't want to do that. It's no fun just doing one, and I would like to try to avoid that. So I'm going to start employing some properties here to help me out. And one of the first properties that I'm going to note is that if I differentiate a polynomial, right, piece, derivatives reduce the order of the polynomial by 1. Right? So I have an x of t that has linear functions, so there's going to be some t terms in there. If I differentiate that guy, those t terms are going to just become constants. Constants wouldn't require an integration by parts. So I'm going to create a new signal. I'm going to call this guy g of t, and g of t is just going to be equal to the derivative of x of t. Okay? And what do I know about that? If I plugged in what was x of t in terms of its Fourier series coefficients, we could go ahead and do that. That would be a derivative on what was the Fourier series synthesis equation on this. Well, it's going to be a sum, right? K equals minus infinity to infinity, and I would have had my cap x of k's, and I would have had e to the jk omega naught t's in there, something like that. If I took the derivative through that, derivative of the sum and sum of derivatives, so that's going to be a summation k equals minus infinity to infinity. I don't have to do all of this. I'm going to just do it this single time. I get an x of k, derivative of that exponential gives me a jk omega naught, and I'm going to have an e to the jk omega naught t. So this looks like a Fourier series for a waveform whose Fourier series coefficients are given by xk times jk omega naught. Of course, I knew this already because we have the derivative of differentiation and time property of the Fourier series. We know that if we have an expression of a signal equaling the derivative of another signal, right, that the Fourier series coefficients of one is equal to the Fourier series coefficients of the other, right, times that frequency variable jk omega naught. And there we see it. This guy is my gk, right? This is just overall, right? This overall piece here is just my Fourier series of the function g, right? And whatever leads that exponential must be my gk. So in a way, I've kind of already just proven in an indirect way the differentiation and time property, but it does tell me that, hey, if I can find g of k, I can get x of k for free just by multiplying or dividing, depending which one you want to get, by the factor jk omega naught. That seems to be a good deal in the bargain. Let's go ahead and sketch out what the signal g of t looks like. So I'm going to go ahead and give my axis again, and I'm going to throw some axis in here. We know that the main period we were dealing with here was -1 all the way out to 2. If I go back to my original signal and I differentiate that first piece, that thing is rising 2 for a run of 1. So its slope is 2, and that's a constant slope over that interval -1 to 0. So I'm going to have in that derivative, right, I can come up 1, 2 units, and I know that it had slope 2, right, between -1 and 0. Now going from 0 to 2, right, I get that negative slope. So it drops 2 over 2. That's a slope of -1. So I would have a constant slope of -1, right, for the interval, right, something in there, 0 to 2. And then this thing's going to repeat, right? We know that that guy's going to repeat, and it's going to have some repetition over there because it was a periodic waveform before. But over the interval -1 to 2, this thing no longer looks like a sawtooth. It looks like a square wave. In fact, it's not that far off from that preliminary waveform we did. So you have an idea of maybe where we're going on this. So what do I know? This whole thing is my little g of t, right? This whole thing is my little g of t as a function of t. And we had already expressed that little g of t was equal to the derivative of x of t. And if I looked at the Fourier analysis on that, that tells me the g of k's is equal to jk omega naught times my x of k's, which means that if I want to get my x of k's from g's, I can say x of k equals g of k by jk omega naught, right? So as long as, well, there is one potential problem here. Look at that k in the denominator. So this thing is for k not equaling 0. If you put k equaling 0 there, that thing would blow up to infinity. Fortunately, we don't really care about the k equaling 0. What is k equaling 0? That's DC. What happens when you differentiate a signal, right? What happens when you differentiate a signal that has a DC component? The DC component disappears anyway. So just because I differentiated, this expression here would not be good for DC to begin with, because I lose it under differentiation. I'll have to find DC separate, just like I would have before. We'll handle that one a bit later. So we have an expression for the x of k's based on this g of k. So let me ask you, if we didn't know anything else, which signal would you rather analyze to find the Fourier series coefficients? Would you rather look at this triangle sawtooth waveform that would require 2 integration by parts, or would you rather look at this piecewise flat function, which would require 2 integrations, but they're both just integrations of exponentials? I think I know most all of us would absolutely prefer this one. The calculus there is just simpler. That's the power of these properties, right? And the power of the properties is that they can save us a whole bunch of effort. Well, we're not done yet, so I'm going to go ahead and in this particular case, I'm going to continue going on this. I'm going to create a new signal, and it's the same sort of game every time. I'm just doing some manipulations on the underlying signal so that I can get it in a simpler form. If I take h of t and say it's equal to g of t plus 1, what would that give me? I'm going to go ahead and sketch it out because sometimes the sketches are the things that are going to help us the most. So we're going -1, and we're still looking over just a single period. So to 2, we know it repeats out of that. So you can leave those dots out there, but we don't have to really draw it. Previously, it was 2 from -1 to 0. So if I add 1 to that, that's going to be 3. 1, 2, 3, come up 3 on this. So I'm going to come up 3, right? And then I'm going to come back to the other side. It had a value -1 between 0 and 2. If I add 1 to that, it's just going to be 0. So now I have a waveform that instead of being 2 over a third of it and -1 over 2/3, this guy is just 3 over a third and it's 0 everywhere else. Which would I rather take the Fourier series of those two waveforms? Absolutely would prefer the one involving h of t, right? Because it's only got one piece I'd have to integrate. The other part being 0 doesn't come into play at all. So instead of doing 2 kind of easy integrations, this one would only require 1 easy integration. Absolutely a bargain in the process. The trick, or the thing we need here, is we need to know what this guy looks in the transform domain. Well, the transform of h is just going to be the Fourier series coefficients, h of k. On the other side, we get g of k. Linearity tells us that a sum of signals gives me a sum of their transforms. And what's the transform of a DC signal? Like 1? Well, that's easy, right? We know that that is just a delta function at 0, right? DC has frequency concentrated at k equaling 0, so I can put in a little Kronecker delta function. So I can put in delta k. You could have, if you wanted to, preferred, you could write this as delta k. We just get single DC content. That means a one-strength DC signal, right? It's DC because delta function's non-zero only at k equaling 0. That's DC. So I can back substitute here, and I can say gk, right, is equal to hk minus that Kronecker delta function, something like that. And then what can I do? I can take that guy and put it up into there, and I can find my x of k's. I'm not going to keep really, well, it's okay, I guess I can. So if I go back and resubstitute up on that, what do I get? I end up getting x of k is being equal to then h of k minus delta k, right, by jk omega naught. So now if I have h of k, right, I can get my x of k's, and h of k is way easier to get than was either x or g. Well, I don't want to stop here. I want to continue with this. One of the things I'll notice is that I have a 1/3 duty cycle DC offset square wave, which I had just studied at the preliminary math on here. The only difference is that my preliminary math required that square wave be centered at 0. This one's not centered at 0. So if I shift this over just by a half unit, I'm going to get this to look very, very similar to what we started our preliminary math with. So I'm going to create yet a new signal. I'm going to call this guy I of t. I of t is going to just be h of t minus a half. What does that kind of look like? Well, we can sketch that out as well. So I'm going to just get now, right, my unit 3 height going from, in this particular case, minus a half to a half. And then if I came over here 3 units later, I get another pulse there of width 1, and it would just keep repeating something along those lines, right? So my IT now actually looks a lot closer to what I started out preliminary math, little p sub tau comma t naught of t, right? Something like that. What does the Fourier of that equation do? Well, a shift in time gives us multiplication by an exponential. So I of k, if you just check out the property tables or the property sheet that's on the formula sheet on the Blackboard site, you get h of k e to the minus jk omega naught times the shift, 1/2, right? Something like that. Or if I back substitute that into all the other stuff, I get x of k, right, being ik, right, e to the minus jk omega naught by 2 minus a delta k all over jk omega naught. So as long as I can get that I of k, I can get x of k. Okay. Well, I'm just about done. The only difference between I and my little p sub tau comma t naught of t is that this guy is 3 units in height, where my little p was a single unit in height. So what do I know? I know that a 1/3 duty cycle periodic pulse train, right, which I studied before, is just going to be equal to 1/3 of my IT. Linearity helps me take care of this, and so if I look at the Fourier transform of that guy, I'm going to get my PKs as being 1/3 of the IKs, or I could say from that IK, right, is 3 times PK, something like that. And then I can do what? I can take that guy and plug it in there, and I would have everything good to go as far as finding all the non-DC terms in there. Perfect. Sounds like a good idea. Just to complete this out and make sure we've got it, once I've done this, once I've scaled that other guy by a factor 3, what do I get? I get a height 1 going from minus a half to a half, and then it just sits there and it repeats every 3 times over, right? And it just keeps going. And that was my 1/3 duty cycle DC offset square wave, which we'd already analyzed. And we know that, right? PK is known. That's what we started the lecture out with. So we can use that directly. The only thing we need left is we need to know what is x of 0, right? What is the DC content? What is the DC content in this case? Well, this particular one, you could do the calculus, but we can also, in this case, just visually get it. I can see that directly in there, that just because we've got all those straight lines in there, the DC value in this guy is 1. So in this particular case, I can just sit there and write it out directly. X0 is equal to 1. So I can pull all these together, and I have my final expression. I can come in here and I can say my x of k, right, is equal to, and I'm going to get a 1, right, for k equaling 0. And then I'm going to go ahead and plug in all of these other things. And I would get a 3 cat p sub k e to the jk omega naught by 2 minus a delta function all over jk omega naught, right, for k not equaling to 0, with, right, my pk from before. That was just that sinc function, right? That was a sinc function. It was a sinc type function. Okay, Well, we can make mistakes doing properties, just like we can make mistakes doing the calculus. So we probably do want to check that. We'll check that here in a second. But I would suggest here that this is a whole lot easier than doing our double integration by parts in this case. We just did some really simple kind of manipulations, utilized some known results for my properties, and I was able to get these Fourier series coefficient x sub k, right, without any integration whatsoever, other than the mental integration I did for the DC part. Okay, let's take a look at what this looks like. You'll be given this code. I'll send it out with the lecture material as well later on. So I've got some code in here. In this first example, I go ahead and I set things up. I clear out the workspace and all that sort of stuff. I set up a parameter. I'm not going to do too many terms in this case. I'm going to go ahead over a frequency from -5 to 5, so I'm only going to include up to the fifth harmonics. I set up the on time tau equaling 1, the period equaling to 3. I set up my omega naught just like we did before. I go ahead and define pk as we had derived at the beginning of the lecture, so tau by t naught sinc function, k omega naught tau by 2 pi. So just a reminder that we defined the sinc there in a way that we could use the MATLAB function. That's why I did it that way. And then I do what? I create that signal I of k as 3 times pk. That was the last step that we went through, and then I'm just going to work my way backwards. H of k, right, is just I of k times an exponential that was corresponding to the shift case. I'm going to have G of k equals H of k minus k equaling 0. That k equaling 0, that relational operator there, is just a quick and easy way of getting a little Kronecker delta function, so that's that delta part. Then I'm going to go ahead and let my xk, for all the non-DC terms, be that gk divided by jk omega naught, right? And then I'm going to go ahead and set the DC term. After I do that, I'm going to go ahead and plot out the spectra so I can take a look at what they look like. And then I'm going to go through some loops and I'm going to construct that. So I'll set up a waveform over 2 periods, and then I'm going to just go term by term in a loop and add in each one of those exponential terms. So the Fourier series coefficient times the complex exponential on those guys. And then I'm going to plot everything out. What does that look like? Well, we go to our next page, that sort of stuff. First, the magnitude and phase spectrum. The magnitude spectrum, there we see that DC value of 1. So we know that DC, in this case, it seems to be the biggest. It is a DC dominant signal. And then we get rapid drop off of the Fourier series coefficients. There certainly are Fourier series coefficients out here, but this is a very DC dominant signal. The phase is pretty complicated, not much that we're going to be able to tell from the phase plot. It's nothing simple, so I don't think you can look at that and really say, ooh, that set of phases corresponds to this sort of little bit soft-looking sawtooth waveform. We're just not going to see that, but we can see it through the reconstruction. When I go back through that reconstruction, this is what we get. Remember, this has only got DC plus up through the fifth harmonic, and this is a really good approximation to that sawtooth waveform. It definitely lines up with the underlying real signal, and in particular, it does really great in these middle areas, right? That's where the signal is pretty smooth anyway. About the only place that you see some error is at those sharp edge tips. Well, what are those sharp edge tips? That's high frequency, and with only 5 harmonics in there, I'm not including enough high frequency to probably do well there. This particular signal, because it is functionally continuous everywhere, not only does it meet all Dirichlet conditions, but it has no jump discontinuities. If I went out to an infinite number of Fourier series terms, I would get pointwise convergence. It would line up for each and every point exactly, and it doesn't take too many for it to do a pretty dang good job. Okay, so we're going to go back to the lecture, and we will do one more example. This first example, like I said, was primarily for ensuring that we got an idea of the different ways to use properties. The second example, so example number 2, this is going to be all about efficiency. I don't really want to sit there and have to come up with preliminary math and try to think how things relate to these kind of hard to see waveforms. This one's going to be trying to be very efficient about things. And in this particular example, I will have to make use of one known transform, but it was the easiest of all, and so it's one that we've already looked at. If you recall, we had looked at a case of having a bunch of delta functions. So we have this Dirac delta train, right? We looked at this previously. So it's a Dirac delta train with period t naught. And when we did the Fourier series on that, we found that the Fourier series coefficients were just 1 over t naught. So a delta train went to a constant spectra. The Fourier series coefficients were all equally sized. All frequencies are equally in presence on this particular signal, at least those harmonic ones that make up this periodic waveform. Okay, so we would like to now do a different one. And so I'm going to take a look at a different waveform. And this one's going to be a little harder. It would definitely be harder if we didn't do this with properties. So I'm going to go ahead and take a look at this particular guy. I'm going to let this thing, I'm going to look over from minus pi by 2 to pi by 2. So I'm going to have a pi periodic waveform. And that periodic waveform I'm going to call x of t here again. And so this particular waveform, I'm going to go ahead and let it be something that is going to really have most of its action going over the middle part here. So from, let's call it minus pi by 4 to pi by 4, this thing is going to be something that's kind of a linear looking function, and it's just going to look like that. And then it's going to return down to 0 after that, and then that whole waveform repeats. It is a form of sawtooth, right? It is a form of sawtooth, and I'm going to let this have a height 1. So it's not a slope 1, but it is a pi periodic sawtooth. If I did maybe a little bit further away view of this guy, right, we'd have this little saw piece here, and then we'd have another little sawtooth piece, and then we'd have another sawtooth piece, and we'd have another sawtooth piece. It would be something like that. So it's a little sawtoothy kind of waveform with gaps in between. So a gapped tooth saw blade. A couple things that we might get out of this: omega naught equals 2 pi by t naught. My t naught here is pi, so I'm going to just get omega naught being equal to 2 rads per second is the fundamental frequency on this guy. Okay, so if I wanted to find the Fourier series coefficients of x, if I wanted to find the x of k's here, I could do it through integration by parts. There would be no doubt about that. But I would like to do this without any integration. One of the things I first might notice is, what is x0? x0 is just 0. We can see that. This has no DC component. That one side of 0 over here, that area is completely canceled out by that area, right? The net DC on this signal is 0. So we don't really have to worry too much about the DC signal on this case. We're just worrying about the non-DC terms in this particular case. We could do it by doing integration by parts. We'd have a linear function, right, times an exponential. You could do integration by parts, but I don't want to. So let's go ahead and use our old friend, the derivative on this. So let's go ahead and differentiate that signal and see what I get. So if I differentiate that signal, that should reduce, right, that linear term to a flat term. So that should help get rid of that need for integration by parts. And so this first part, right, this slope here, we can see that it rises 1 over pi by 4. That means it has a slope of 4 by pi. So when I differentiate that, slope is nothing, derivative is nothing more than slope. So I know that I have a constant flat slope, right? Going from, well, we have minus pi by 4 over there to pi by 4 over there. This is all a function of t. We do know there's some periodicity in there. We're only looking at the period, so that's fine. So I'm going to have this derivative here going on, and it's got a height here of 4 by pi. So we're letting what? We're letting y of t equal the derivative of x of t. And we know that this is nice because if you differentiate in the time domain, when we go to the transform domain, yk is equal jk omega naught x of k's. So if I can find the YKs, I can get the X of Ks really easy, except for a DC, which we know is 0 in this case. There is one part I've forgotten though, right? We had in this particular case a sharp edge and another sharp edge. And we know that when we get those jump discontinuities and we differentiate, we get delta functions, right? That was something we studied early in the semester. So as I'm moving along this waveform from left to right, I hit this jump discontinuity. I go down a total value of 1, right? So that's going to give me a delta function there going down, height or weight of -1. As I look up here again, I then start crawling up on that straight line piece, and then I drop down again. And how far do I drop? I drop 1 unit. So when I do the differentiation operation, I'm going to get another delta function there of 1. So my y of t, right, has a flat part, pi, 4 by pi, going from minus pi by 4 to pi by 4, and it's got a couple of deltas. And remember, it's periodic. So there's actually a delta train, right, and another delta train, each shifted from the origin, and then we've got that kind of box function in the middle. Now I could use the p sub tau comma t naught of t, and I could just solve it right here, right now, but I would like to not try to use that or try to memorize that sinc function. I don't want to commit that to memory because another differentiation will help me complete this out, so I don't even need to know that. So I would like to differentiate a part of this waveform. If I differentiate the whole thing, I'm going to get into trouble. If I differentiate this, if I take this guy, right, and if I differentiate, if I do a ddt, I get in trouble. I get in trouble, right? So I don't want to be doing differentiation on the delta functions. However, if I take this part and I do ddt, that's okay. That's okay, right? So what I'm going to do is I'm going to do something like this. I'm going to say y of t equals some delta part, right, plus some non-delta part. So I'm going to let y of t, right, which we knew was our dt of x of t, I'm going to let it be some non-delta part. I'm going to call that z of t. So if I come back up here, what I circled in green, we're going to let that be little z of t, okay, something along those lines. I'm going to let that be z of t, plus then what? Well, I guess I won't do it as a plus because they were weighted negative. I'm going to do a minus. There's going to be a delta train with period pi, right? And it's going to be shifted by pi by 4. And there's another delta train, and it's going to be shifted the other direction, plus pi by 4, something like that. So I can create that signal y, which was the derivative of x, right? We knew that this guy was d dt of x of t, right? That y has a delta part and a non-delta part. So these are the delta part, right? And this is the non-delta part. And what I'm going to do is I'm going to differentiate just the non-delta part. Why? Because then I don't have to do any integration with that or have to use that knowledge of what a pulse function is. So let's continue this guy. And we're going to get then what? We're going to get, oops, I don't want to do that in that color. Let's do it black to black. Let's do this. Let's say u of t equals d dt of z. That's a very bad z. Let's try it again. Z of t, right? Something along those lines. So I want to just differentiate that square pulse. Well, it's flat slope everywhere. So it's got a slope of 0 almost everywhere. The only action on that is going to be when I have that jump discontinuity here going up and then coming down on the other side. Those are the only parts that I'm going to see coming through on that differentiation. So if I take a look at a sketch of my u of t, right, I know that I was going to get a upshot, so an up delta function or an up delta train, and it went up by 4 by pi, just because that was what the slope was before. This is all my function u of t. And then I'm going to come back and I'm going to fall down the other side with a delta, and that's going to be minus 4 by pi. These are all functions of time. And this guy occurred at what? Well, this was pi by 4, and this was minus pi by 4, something like that. So u of t is just purely equal to delta function. So I could say something like u of t equals d dt, right, of z of t. And it is just these delta trains. Now there's a 4 by pi weight on it, and I'm going to get my delta train period pi. And the first one, well, we can shift that guy by pi by 4. And then we are going to subtract a pi by 4 by pi. And there's another pi periodic delta train, except for it had to be shifted to the right. So a minus pi by 4 on there, something along those lines. Okay, so what do I have? I have taken an original signal x of t gap-toothed saw wave. I've differentiated it once. That got rid of the linear part and made it all flat with deltas. Deltas are easy to transform. I didn't want to mess with that square part, so I differentiated that non-delta part, and I got this u, and that just gave me another set of delta trains. From lecture, right, from previous lecture, and because I reminded us just earlier from lecture, we do know what? We know that delta tilde sub t naught of t, right, goes through that Fourier series operator give me a 1 over t naught. And because t naught in this case is pi, we're just going to get a 1 over pi, and that's true for all k, right? Something along those lines. I think we have everything that we need to. We knew that cap x of 0 was equal to 0. That was by inspection, right? By inspection. And we can find x sub k for k not equal to 0 by these properties use, along with that knowledge of what the delta function does. So what do I know? I can use linearity, right, and time shifting to find the transform of my u signal. So u sub k. My u sub k is equal to what? Well, it was a delta train, and that delta train had a 1 by t naught. There was 2 delta trains in there. They each had weight 4 by pi, right? They will all have a 1 by t naught. That's just the Fourier series coefficients. But because they were shifted in time, we get multiplication by exponential. So I'm going to get an e to the jk omega naught pi by 4 for the 1, and then a minus 1 by t naught e to the minus jk omega naught t by 4, pi by 4, something like that, omega naught t by 4, which is pi by 4, something along those lines. If I go ahead and look at that, I have an e to the j something minus an e to the minus j something. That's really close to a sign, so I can combine those together with a sign. So I'll need to divide by a 2j, and that means multiply by a 2j outside. So that 2j times the 4 is going to give me an 8j, right? And what I'll end up with here, because t naught is equal to pi, I can pull that 1 by t naught out, and that's going to give me a pi squared. So I'm going to have an 8j by pi squared, and then I'm going to be left with that sine function of what? K, and then omega naught, right? In this particular case, my omega naught, if we go back up to what we were looking at, I think we did compute that somewhere. Omega naught was just 2, so I could certainly plug that guy in there. If I put the 2 in there, I'm going to get a k 2 pi by 4. That's going to give me a k pi by 2. Something along those lines. So the UK has very easy Fourier series coefficients that we got just by linearity and time shifting, knowing that it was constructed out of those shifted delta traits. Using the time differentiation again, time differentiation, we can go from the u back to the z. So I knew that u is equal to the time derivative of z. So that means my u of k equals j omega naught k, right, times z k, of which I can then get and solve for zk. Zk is going to be, well, omega naught was 2, so I'm going to get a 1 over j2k, right, times my my other function, which was an 8 by j pi squared sine k pi by 2, something along those lines. So if I clean that up just a little bit, the j's cancel. The 2 will go up into the 8 and leave me with just 4. And so I'm going to get something like a 4 by k pi squared sine k pi by 2. That gives me my z. Okay, well, with that z, I can again use some properties. I'll use linearity, and time shift properties. So I'm going to go ahead and use the linearity and the time shift properties, and I'm going to be able to back out my y of k. If you remember, y of k was made up of the non-delta part. That was just the zk, which we already know, right? And then we had a couple of delta trains, and we know how to handle those delta trains. Those delta trains have transforms 1 by t naught, and because they were shifted, we're going to get some multiplication by exponentials. These ones were both like simple shifts of pi by 4. So I'm going to get an e to the minus jk omega naught pi by 4, and then I'm going to have an e to the jk omega naught pi by 4, only different in the sign because one was shifted right and one was shifted left. This term on the right, e to the j something plus e to the minus j something, that looks a lot like a cosine if I just divided by 2. Okay, so what do I get out of this? I get a yk. Go ahead and plug in what is zk. Zk in this case was what? It was 4 by k pi squared, and then we had that sine k pi by 2. We know t naught was pi, And I know that I need a 2 in the denominator to get that right-hand pair of exponentials to be a cosine. So I'm going to have a minus, put a 2 up in the numerator. I'm going to still have that t naught, which we know is pi in the denominator. And then I'm left with an e to the j something plus e to the minus j something over 2. That's just a cosine of the something. And the something here is k omega naught pi by 4. Omega naught is 2, so that's going to be a k pi by 2. Okay, so we're almost done. That was our y. If you remember how we got y by taking the time derivative of x. So we can go time differentiation property again. And we know through that time differentiation property that my y of k is equal to j k omega naught x of k. And I can solve for that, and I can get my x of k then being equal to what? It's going to be a 1 by j to k times then 4 by k pi squared sine k pi by 2, and I'm going to have a minus 2 by pi cosine k pi by 2. Okay, something like that. Now if I just do a tiny bit more cleanup, I can get the final result, at least in a nicer form. I'm going to have x of k equals 1 over, and I'm going to have a j k pi, and then I'm going to have a 2 by k pi sine k pi by 2. That looks a lot like sync, right? Minus a cosine here of k pi by 2. Something along those lines. That is for k not equaling to 0. For k equaling 0, I get x 0 then equaling 0. Okay, so I do have a final expression for all of this stuff, and I didn't have to do a bit of calculus. Think, if you had gone through all that integration by parts and simplified, you would have had to work your way to getting something like that. Not easy to do through the calculus. Here, just doing it by properties, never had to do integration by once, just did some repeated differentiations, never differentiated a delta function. That'll get you into trouble. So sometimes you split it into delta and non-delta parts. This will work in general for virtually any kind of signal. So it's a very nice technique. Let's make sure that it's correct. So I'm going to go back over to my other one. Continuing with that, it has the second set of code in the same file that I'll send you. I'm not going to go through it here. You'll see that I just basically define my x of k's in terms of what I just derived. And that's this part here. So I just derived or define those x of k's in terms of what I derived. I go ahead and plot out the spectrum. Then I resynthesize the waveform, and I plot that out to make sure it looks like what I expect it to be. So what does it look like? Here is the magnitude and phase spectrum. This is a tougher signal to synthesize, right? If you remember what the signal looked like, right? That signal looked like these little sawtooths, and they kept repeating, and there's that gap in between there. There's all that sharp edge there. There's that sharp edge there. There's this transition from sharp to flat and sharp to the slant of the linear part. All those sharp edges are high frequency stuff, and that high frequency stuff means there's going to be more high frequency terms that are significant. So we're probably going to have to go much higher than k equaling 5 like we did in the last example. We're going to need a lot more than that. So I went ahead and split out k here, the frequency terms for looking at the magnitude spectrum and the phase spectrum, going out to something like the 40th harmonic. And we definitely see that there's some content that is pretty slow to decay in there. This is a signal that has no DC term, but the first harmonic, right, that's these two pieces in there. The first harmonic is the biggest coefficients in there, so those are going to be the most important. There's some other ones, though, nearby that are pretty significant as well, and then they get less and less important as we go along. Phase, nothing that we can really tell much by that. It's more regular than the other one, but in the end, not a lot we can tell on that. Resynthesize this guy. Here's an example with those 40 terms, and we absolutely see that this thing is converging to that gap sawtooth. We do see that ripple, that overshoot that's typical of Gibbs phenomenon near points of discontinuity, and so it's looking very, very good. We have good confidence that we have the right values. Okay, so I think we've gotten through the properties that we need to do. That's it for this lecture.